Good morning, friends and dear students. I really feel overwhelmed that a lot of students are seeing my videos and giving a lot of comments on that. I am here for my course Flight Mechanics. This course is for the 4th semester Aeronautical Engineering student from the Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. My today's topic is climb performance, which is in module 3 in the syllabus. I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. Today's my topics are climb and descent comparison, types of climb, different angles during climb, rate of climb, power available and the power required. These are the topics which I am going to take today. These are the very basics for any climb flight phase. In further lectures, we will be discussing about derivations of equations and other things. In today's very basics of the climb is discussed in this lecture. So, again, as I do every time, a regular flight of every conventional aircraft includes a climb and the descent. So if you see any aircraft, this is your takeoff, then this is the climb, and then this is the cruise, then this is the descent. So this is the climb, and this is opposite to the climb, it is called descent. Descent. Okay, so these are the two phases. It is going upward and this is coming downwards, and then here some loiter, then it is landing. So every flight will have to climb and then it has to descend. Climb normally follows takeoff. So this is the takeoff and here is the landing, and descent is necessary prior to the landing. So to land, first aircraft has to descend. So that is the requirement. For the takeoff is the climb, and for descent it is landing. Climb is the gain of altitude compared to a reference level, but descent is the loss of altitude. Climb is the gain of altitude, means it is during the climb altitude is increased, and during descent altitude is decreased. So altitude here is decreasing and here it is increasing. So height, it is a ground level and it is some height, from some height to the ground level. So it is opposite in nature. In climb aircraft, potential energy PE is increased. So if the H is increasing, MGH is increasing. Here H is decreasing, so MGH is potential energy is decreasing. But in the descent, the same PE is consumed. Climb need a source of energy. Some engine power is required for the climbing. That is primary the engine, but descent does not need any source. It is not required. Its gravity is sufficient to make the aircraft descend. When an aircraft gains altitude without consuming energy or without employing engine power from rising warm air, it is referred to as a soaring. So sometimes this climb may happen due to the change of atmospheric temperature. If the temperature is getting heated up, your aircraft or your body or anything can go up. You might have seen during the summer season some tornadoes, small tornadoes are there it is circulating and it is things can go upward. So like this also it can happen. Types of climb and ceiling. In climb analysis, we focus mainly on three major parameters. That is, first is the maximum rate of climb, that is the fastest climb. Maximum rate of climb, and it is also called the fastest climb. Maximum climb angle, that is steepest climb. And minimum cost climb or most economical climb. So these three are very, very important parameters for any aircraft that we have to calculate as per that. Maximum rate of climb, that is called fastest climb. Maximum climb angle, that is steepest climb. Minimum cost climb, that is the most economical climb. At 4 altitude, the rate of climb has defined value, a defined value. So we have some altitude, and for each altitude we have some defined rate of climb as mentioned in this. At absolute ceiling, the maximum rate of climb is 0. So this is if you are flying at a absolute altitude, this is the absolute altitude. In this, if your aircraft is here, no climb. Aircraft will not climb. That is called the absolute climb. At service ceiling, below to this, somewhere your aircraft, this is the service ceiling. Here you will have rate of climb 100 feet per minute or 0.5 meter per second. That is called the service ceiling. At cruise ceiling, somewhat lesser height. This is the cruise ceiling. It will have 300 feet per minute or 1.5 meter per second. So the cruise ceiling is that height where your aircraft will have 300 feet per minute or 1.5 meter per second climb rate. Next one is the combat ceiling. It is for the fighter aircraft. The maximum rate of climb is 500 feet. This is the combat ceiling. Here you have 500 feet per minute. This is the 2.5 meter per second or 500 or 2.5 meter per second. So these are the 4 types of ceiling of aircraft, and that we have to make sure that this is the highest one, this is lower than absolute, this is lower than service, and this is the lower than the cruise. So like this we have to understand. Now different angles during the climb. So rate of climb is the vertical component of the aircraft airspeed. Rate of climb depends on the 2 parameters, that is aircraft airspeed V and the climb angle gamma, as it is represented here. This is the climb angle. It is angle between horizontal and the direction of the aircraft. The climb angle gamma is defined as the angle between the instantaneous flight path direction, the direction of the relative wind, and the horizontal. So this is the horizontal and this is the relative wind. This angle is called the gamma flight path angle. The pitch angle theta is the sum of the angle of attack and the pitch angle. If the angle of attack is here alpha, this is the gamma. So from here to here it is the theta. So this theta is equal to gamma plus alpha, where alpha is angle of attack, gamma is flight path angle, and theta is pitch angle. Okay, so this is the definition of different angle, theta, gamma and the alpha. So here it is mentioned that theta is equal to gamma plus alpha. So now depiction of angle of attack and the climb angle. So climb angle and angle of attack, the aircraft in cruise, the aircraft in climb with zero angle of attack. A condition is the aircraft in cruise. The B is the aircraft in climb and the zero angle of attack. C is the aircraft in climb with an angle of attack. So this you can see here. We have the first case, the aircraft in the cruise. So there is only angle of attack. There is no climb angle. The aircraft in climb with zero angle of attack. The second case, it is a climbing, means there is a gamma, but no angle of attack because the air is in the same direction. Here if you see, air is in this direction and it is the direction of the flight. So it is an angle of attack. But if the direction of the air is in the direction of the aircraft, alpha will be 0. Only gamma will be there. Gamma will be there as shown here. Next case, the aircraft in climb with an angle of attack. So in this, there is an angle between relative wind V and this aircraft. So here is the angle of attack. This is the gamma. So here theta is equal to gamma plus alpha. So this is the climb with an angle of attack. How the direction plays very important. Wind direction plays very important role, and it is shown in this 3 diagram. You can see again, it is the center line, it is the fuselage reference line. If it is aircraft is flying in this direction and your wind is in this direction, so there is a angle between fuselage reference line and this direction of from the horizontal and the flight path. So this is called alpha or angle of attack. And if this direction of the flow is in the direction of the fuselage reference line, there is no angle of attack, and this is called the flight path angle from the horizontal. The angle between horizontal and the fuselage reference line is called the flight path angle. In the third case, in the C, if you can see here that the flight path angle is not in the same direction as the fuselage reference line, but there is some angle alpha, this one alpha, but there is also making this gamma. So this gamma plus alpha is equal to theta. We can say that aircraft is pitching with theta. So that is very much important to understand this all concept. The maximum angle of attack of most of the aircraft is frequently less than 15. So angle of attack is mostly less than 15 degrees. Because after 15 degree, aircraft wing will stall, lift will be reduced, drag will be increased. If I make a plot for this, so this is the nearly 15 degree. After that here, lift versus alpha, so lift will be reduced, and if I make the plot of drag, it will increase like this. So if I make, so it will go like this. This is the drag and this is the lift. So that is we have to make sure that we should not fly beyond this angle of attack. But the maximum climb angle is often 10 to 30 degree. Climb angle is always much more than the angle of attack. Now we see the rate of climb. This ROC. So the ROC is the rate of change of altitude per unit time. Means how much distance vertically this this distance h per unit time. If the aircraft is here, how much it is going upward per unit time, it is called the rate of climb. Rate of climb is equal to dh by dt or h dot. So this we can see here that how much it is vertically it is moving h. So that is the per unit time. dh by dt is equal to h dot. Here h is the altitude or height and t is the time. The aircraft in this figure is climbing with a constant acceleration a. Based on the Newton's second law and using previous equation, we can write the equilibrium of the forces in the direction of flight as, if you see here, this is the thrust. So thrust cos it plus alpha minus d, it is in opposite direction, minus w sine in this same direction. Here also w sine gamma. So t cos alpha, t cos in bracket it plus alpha minus d minus w sine gamma is equal to ma m dv by dt. So assume that the thrust line is in the direction of the flight, ignoring the effect of angle of attack on the engine thrust. For more simplicity, we assume that all forces are passing through the aircraft's center of gravity and aircraft angle of attack is 0. So if alpha is 0, it is 0, like this. So we can say that t minus d minus mg sine gamma is equal to m dv by dt. And if the acceleration is 0, we can write that this is also 0. So the relationship between forward speed v and the rate of climb is given by the figure. So this you can see here x, h, and this is the v here. So we can see that v sine gamma is equal to h by t or h dot. So this is called the rate of climb, v sine gamma. This is the rate of climb. Multiplying both sides by v and substituting equation 5 into 4, this we will eat that if we multiply by v. So tv minus dv is equal to mg h dot is equal to mv into dv by dt. We have multiplied by v. So here we will get that t minus d into v is equal to d by dt mgh plus half mv square. So this we got one equation that t minus dv, this is called excess power, is equal to summation of potential energy plus kinetic energy. So on the right hand side, mgh is the aircraft potential energy and half rho v, half mv square is the aircraft kinetic energy ke, and their summation is total energy of the aircraft. On the left hand side, we have T minus D is the aircraft excess force and T minus D into V is called the excess power. So we can see that a climb results in a change in the total energy of the aircraft. This includes both potential energy and the kinetic energy. If the aircraft is climbing with a constant airspeed, the excess power is equivalent to the rate of change of potential energy. Power available, PAV, and the power required. These two terms we have to understand very well. What is the power required and what is the power available? The product of engine thrust and the aircraft airspeed for a level flight is referred to as a available power, means how much thrust engine is producing into the velocity. Similarly, the product of aircraft aerodynamic drag D and the aircraft airspeed for a level flight is called the required power or P required, PR. Thus, the excess power Px is a difference. Px is equal to T minus D into V is equal to TV minus dV, P available minus P required. So, if you see in this plot, this is the power required and this is the power available, and the difference between power available and the power required at particular instant, these are called the excess power here. All these lines here, these all are the excess power. Okay, so this we have to very well understand. So now this figure shows the variation of the available power and the required power with air speed. As the excess power is increased, the rate of climb is also increased. So as much you have the more excess power, the point here you have this is the minimum power required, this and this is the different points here. Governing equation for the climb. The governing equation of the motion for this climb, as this we have seen already, that T cos IT plus alpha minus D minus W sin gamma is equal to MA. This you can see here, that what is the meaning of this. T is here, D is here, W, so here W sin gamma, and if T is having some angle, this is the alpha here, this is IT. So accordingly we can draw the equation of motion. So L plus T sin IT plus alpha minus W cos gamma is equal to M d V sin gamma by dt. And we can see here, we assume that the aircraft has a point mass and the thrust line coincides with the flight path, that is IT is equal to 0. The aircraft angle of attack is also assumed to be negligible, that is alpha is equal to 0. Then we consider a steady unaccelerated climb with a constant speed v. Therefore, the right hand side of the equation 9 and the 10 will be 0. By these simplifying assumptions, equation 9 will be T minus D minus W sin gamma is equal to 0, or sin gamma is equal to T minus D by W. In the Z direction, the equilibrium of forces will result in L minus W sin gamma is equal to 0. This is another equation. So we can do the analysis of rate of climb. From this equation 12 and 30, following conclusion can be drawn. So what are the 12 and 13? Sin gamma T minus D by W and L is equal to W cos gamma. So these are the 12, equation number 12, and this is the equation number 13. So we can get some conclusion out of this. The climb angle is the function of the thrust and the drag. This sin gamma is a function of the thrust and the drag, and the reciprocal of the weight W. And okay, so this we can see here that this sin gamma is equal to T minus D by W. So this climb angle sin gamma is directly proportional to the thrust and the drag and the reciprocal of the weight. So if weight is more, climb angle will be less. So we should make our aircraft less weight so that the climb angle can be increased, and the difference between thrust available and the thrust required also should be more. Excess thrust should be T excess should be high. The heavier the aircraft, the lower the climb angle. It is weight factor. Lower the drag, more the climb angle. As much you have, the lower the drag, low, the T minus D will be high or Tx will be high. That much your angle of attack will be high. Maximum possible climb angle is 90 degree. It happens when TD is equal or more than W. So if you make gamma 90, so T minus D is equal to W. So if the excess thrust and the weight are same, that time only your aircraft can go 90 degree of the flight. Faster the aircraft, lower the climb angle. This is due to the increase in drag, due to increase in velocity. Light aircraft has better climb performance. By equation 13, we can see that during climb flight, the lift is always less than the aircraft weight. This implies that the main part of the climb capability is based on the thrust. An engine with greater thrust will have higher climb capability. So L minus W cos gamma is equal to 0. So now we will discuss some about the velocities, some velocities in this topic. An aircraft in a climbing flight has the following three velocities. One is aircraft speed or airspeed V, that is the aircraft speed relative to the air along the flight path. So this is the V. Another one is the horizontal component of the airspeed or the aircraft speed parallel to the horizontal. It is called VH. If there is no wind, this speed is equal to aircraft ground speed. This speed is very important in navigation and is equal to the VH is equal to x dot, and this is the V cos gamma. The vertical component of the airspeed or the aircraft speed perpendicular to the horizontal, that is VV. This is the rate of climb. So VV is equal to H is equal to V sin gamma. The left hand side of the equation looks similar. Earlier in this chapter, we defined the required power and the available power. Using those terms, we can write that V sin gamma is equal to TV minus dV by W, or P required minus P available divided by W. So it is not correct. P available minus P required by W. So it is a excess power divided by W. The left hand side of the equation 16 is by definition rate of climb. So rate of climb is equal to V sin gamma. So in the next lecture, we are going to discuss these topics: fastest climb or the maximum rate of climb, effect of the aircraft speed on the rate of climb, maximum rate of climb of a jet aircraft, calculation of climb angle for the maximum rate of climb, direct method for finding climb angle. These are the references which I have taken from Anderson JD, Junior, Aircraft Performance and Design, International Edition, McGraw-Hill's, First Edition, 1999. Isselby, Emmy, Aircraft Performance, Theory and Practice, AIA Education Series, AIA. Any questions, you are welcome to ask to my email, yddwivedhi@iare.ac.in. This is my email. You can send the queries in this. Please do like and subscribe this channel. Please be tuned for my next lecture, which I have given just now. I will be discussing very soon. Thank you very much. Till then, goodbye and see you.
Like, share and subscribe. Hit the bell icon for more updates.